Welcome to the first video of Unit 8, all about chemical reactions. So what is a chemical reaction? So a chemical reaction occurs when the chemical composition of a substance changes. By definition, a chemical reaction is one or more substances are changed into one or more new substances by the reorganization of the component atoms. So what does that mean? It means we start with some stuff and it gets changed around to become different stuff. So how do chemical reactions occur? Collision theory describes the conditions for reactions to occur, and it states that particles, atoms or molecules, must collide in order for a chemical reaction to occur, that these collisions are what cause chemical reactions to happen. What are our evidence of chemical reactions? So there are lots of different ways to know that you had a chemical reaction. We can have a light being produced, like when we burned that magnesium. We can have a precipitate, which is a solid that forms. That's what's happening in this picture right here. We mix two clear chemicals together, and almost like magic, we got a yellow solid that came out. An odor or gas can be released. This can be in the form of effervescence, which is what you're seeing in this picture down here, which is bubbling from the gas being produced. Heat or a flame being produced, like you see happening here. Heat can also be absorbed, meaning that it feels very cold. Water can be produced. You can have a color change along with another change. Color change on its own is often just a physical change, not a chemical change. And the physical and chemical properties of the product are different than the reactant. So let's see how you do. In here we have a match burning. So what evidence is this of a chemical reaction? That's an easy one. Flame being produced. How about in these beakers here? I went with color change because you can see we have a yellow and a green. We can also see that some sort of temperature change is occurring because we have this gas, also gas being produced, multiple ones you could have went with there. In this picture here, what is happening? Vocabulary word, effervescence. We have a gas being produced. Then in this picture, we have a rotten apple. And that's a chemical reaction too, because the ending material, our rotten apple, has very different properties than our starting material. So these chemical reactions can be written in chemical equations. So a chemical equation is a representation of a chemical reaction using the formulas of the starting substances that react and the new substances that are formed. Reactants are what the starting substances are called that enter into the chemical reaction, and you're always going to find them on the left side of the reaction arrow. Our products are the new substances that are formed during the chemical reaction, and we're always going to find them on the right side of the arrow. That arrow means yield, or it's called a reaction arrow, and it separates our reactants from our products. Just a sample equation for you, we have x plus y, arrow xy. X and y are reactants. XY together is our product. Some other signs and symbols you need to know. Some you probably already do. Plus symbol just means plus or and. An arrow, as we already discussed, means yields or forms. If you see a double-ended arrow, that means that reaction is reversible, that it can go backwards as well as forward. When you see this little triangle above an arrow, it means we had to add heat to make that chemical reaction happen. And if you see letters above an arrow, that means some sort of catalyst was used, in this case platinum, because platinum is PT. Next to your different elements, you will also see parentheses with a letter inside, and that tells us the state of matter. S is solid, L is liquid, G is gas. The one you may not know is if you see an AQ in parentheses, that means aqueous, which means whatever product you get has been dissolved in water. So what symbols are used when we write chemical equations? First big one are coefficients, and this is a number we put in front of a substance. You've seen this before when we learned to count atoms, and this applies to all elements in that compound or molecule. Subscripts are those little numbers that we've been using all this time, and that's the number after an element, and it only applies to that one element. As we already discussed, we can also have our states of matter in parentheses, solid, liquid, gas. We can also have aqueous in parentheses. So this brings us to the law of conservation of mass, and it's very important when it comes to chemical reactions. So matter is neither created nor destroyed in a chemical reaction. That means the starting mass of the reactants has to equal the final mass of the products. We can't lose matter during our chemical reaction. So this must be satisfied when describing a reaction, and we satisfy that by a process called balancing, which we're going to be learning all about. All that is happening in a chemical reaction is atoms are being rearranged. They aren't leaving, they aren't coming, they are just getting rearranged. So you have to have the same number of each element on both sides of our reaction arrow. We're going to do that using coefficients. So coefficients show the amount of each substance. It goes in front of the compound and applies to all elements in that compound. Coefficients are used to balance. You can change coefficients as much as you need to get it to balance, but subscripts can never, ever, ever, ever be changed, because that subscript is telling you what compound you have. If you change the subscript, you've changed the compound, and that is a huge no-no. So you can only mess with our coefficients. So if I told you you had H2O, you know that means you have 2 hydrogen atoms and 1 oxygen atom. But if we do 2 H2O, we now have 4 hydrogen atoms, 2 times 2, and 2 oxygen atoms, 2 times 1. So the coefficients show proportions of formula units or molecules involved and the relative amount expressed in moles. So we're going to use those coefficients to balance chemical equations. So in order for an equation to reflect the law of conservation of mass, it must be balanced. That means that the number of atoms on each element on the reactant side must equal the number of atoms of each element on the product side. A balanced chemical equation has the same number of atoms on both sides of the equation. Some tips to remember when balancing chemical equations: you never change the subscripts. You can only use whole number coefficients. You can't tell me 1/2 or something like that. If you don't see a coefficient in front, that means there's a secret one in there. And if you get stuck, try multiplying your first coefficient by 2 and start over. This is only for combustion reactions. We'll be getting to those later, but those are the trickiest ones to balance. So we're going to be doing those last, but something to think about. So what are our rules for balancing chemical equations? First, you need to write correct formulas for the reactant and product. I'm sometimes going to give them to you, but I'm sometimes not going to give them to you, and I'm just going to tell you in word problem format what you have, and you need to be able to read those words and create the correct formula for them. That's why we learned ionic compounds, covalent compounds, and acids. You also need to remember the 7 diatomic gases. These are our Brinkelhoffs. If I just say you have nitrogen, you need to know that means N2. You're going to balance the number of atoms on both sides by adding coefficients. Once again, do not change the subscripts. Some useful tips to try: make an element inventory. I like to keep track by listing out all the elements I have on each side and keeping track of how many I have on each side. It might help you to rewrite water as HOH to help you keep track. Balance polyatomic ions as a group if they appear on both sides of the chemical equation. So if your polyatomic ion remains unchanged, sulfate is on one side, sulfate is on the other side, try balancing it as a group instead of thinking about it as separate things. Balance hydrogen and oxygen last, as those are oftentimes the ones that are the trickiest. So let's look at an example here. We have MgCl2 plus H2O yields MgOH2 plus HCl. So let's look. I have one magnesium on this side, one magnesium on that side. That's pretty good. I want to leave that alone as much as possible. I have 2 chlorines on this side and only 1 chlorine on that side. So I'm thinking I probably want to put a 2 in front of that in order to give myself 2 chlorines. I have 2 hydrogens on this side, 2 hydrogens on here, but that gives me a 3rd hydrogen. But if I multiply it times 2, that's going to give me 4 hydrogens, which means I'm going to need to put a 2 there, and that balances everything up. Let's practice that a little bit more. So I said you'll also sometimes be given a word problem. So let's practice that. You're told aluminum sulfate reacts with barium chloride to form aluminum chloride and barium sulfate. Oh, that can seem really overwhelming, but it's not. You know how to do all of this. What's the formula for aluminum sulfate? What's the formula for barium chloride? You can do this. So let's start off by circling the reactants and underlining our products. All right? So aluminum sulfate and barium chloride are our reactants, and aluminum chloride and barium sulfate are our products. Great. Let's write the formula for the things we've circled and underlined and put them on the correct side of the arrow. If you need to pause this video for a second to do that, do it now. So we get Al2SO43, that's aluminum sulfate. We have barium chloride, BaCl2. We have aluminum chloride, AlCl3. And we have barium sulfate, BaSO4. So the last thing that we need to do is balance the chemical equation. So once again, we need the same number of aluminums on each side. We need the same number of sulfates on each side. We need the same number of bariums on each side. We need the same number of chlorines on each side. So pause this video and try and balance it. All right, how'd you do? You should have left the Al2SO43 completely alone. A lot of times I try and leave my biggest one alone. But I knew I had to balance up my chlorines straight off the bat because I had 2 and 3, and I knew I needed to balance up my aluminums because I had 2 and 1. So I put a 2 there. In the process, that gave me 6 chlorines. So I need to make 6 chlorines over here. That gave me 3 bariums, so I made 3 bariums over here, which in the process balanced up my sulfates. How'd you do? Let's try another practice one. Nitrogen gas plus hydrogen gas under pressure at a high temperature turn into ammonia. I want you to pause this video, figure out your reactants, figure out your products, write the chemical equation, and balance it all on your own. Pause this video and come back when you're done. All right, let's see how you did. So when you circled your reactants and underlined your products, you wrote the correct formulas for each substance in the reaction, and you balanced the chemical equations. If you haven't done those things yet, pause this video again and do it now. Your correct answer should have been N2, because nitrogen's a Brinkelhoff, plus 3H2, H2 because hydrogen is also a Brinkelhoff. Ammonia is NH3. We had 2 nitrogens on this side, so we needed to put 2 nitrogens on that side, so we put a 2 there. That gave us 6 hydrogens, which meant we put 6 hydrogens over here. Hopefully you're getting the hang of this. Come to class tomorrow, ready to practice balancing chemical reactions.